In this video, I will talk about computers and how they can be used to build programs in order to efficiently solve your large-scale numerical problems. So scientific computing, is basically built up of very repetitive numerical calculations on a very large and vast amount of data. And this is very boring work for humans, but computers are really built for this. So they're very good at number crunching and doing things repetitively. So in that sense, we need to be able to convert our numerical methods and numerical algorithms into a set or a list of specific instructions for computers, such that they can be executed efficiently and fast. Now, in the past, computers looked like this. And I'm not talking about the machines on the desks, but up until the 1940s, most of the scientific computing was actually being done by humans. So these humans were given a set of instructions, a set of calculations that they had to do, and they worked through these calculations, and after a while someone came and picked up the papers and gave them a new set of instructions. And this was how programming and computers were being done at that time, actually. Now, a lot changed obviously since then, especially since the advent of the electronic computers. So if we take a look at the computers of today, here we see the top 500 list of supercomputers around the world. This is the top 5 of that top 500. And so every 6 months, this website, top500.org, will compile a list of the most powerful supercomputers in the world. And the currently fastest system is called Summit. It's in the United States. And just taking a look at the specifications over here, well, this is a system which well, it consists of a large set of cabinets within a data center. It holds 2.5 million compute cores and is built up of a combination of CPUs and GPUs. So those are also being used for computing nowadays. The peak performance here is 200 petaflops, which means that it can do 2 times 10 to the power 17 floating point operations per second. So those are additions, multiplications. So that is a huge amount. And also if you look at the power that these things are using, so that is a 10 megawatt power usage. To put this into perspective, 10 megawatt is roughly what can be expected from a utility scale offshore wind turbine. So those very largest wind turbines that are now actually only designing have about 10 megawatts power output in their peak. Now, modern scientific programming languages can be mostly split into two categories: compiled languages, such as these older languages, C, C++, or Fortran. They can be used for most of the heavy lifting because they're very numerically efficient, they're very fast, but implementing your algorithms there can be cumbersome and will take a lot of work. On the other hand, you have interpreted languages such as MATLAB, Python. They are much easier to program, but they tend to be relatively slow. However, within the context of this course, we will only look at interpreted programming languages because, well, we want to be able to rapidly implement our algorithms and test them. So the really heavy lifting is outside of the scope of this course. However, even on the fastest supercomputers on Earth, many problems that we want to solve today are still orders of magnitude too expensive. So this really clearly justifies the need for education and research into computational science because there is a constant need for improved algorithms in all disciplines throughout science and engineering. To close off this part on computers and programming, let's look at a specific concrete example. So we want to write a program that, given a quadratic polynomial in the form of its coefficients a, b, and c, will return its zeros or its roots. In other words, the x such that ax squared plus bx plus c is equal to 0. Now we already have an algorithm described for this, and that's the algorithm we all know using the discriminant. So the first step is to compute the discriminant, and then based on the value thereof, we take certain actions. Now, this program is a program with a clear input, so a, b, and c, and a clear output in the form of the roots x1 and x2. So the most natural way of programming this is to use a function. Now we can easily create a function in MATLAB by clicking on the New button and then selecting Function from the drop-down menu. So this will open an editor window, which provides us with a template which already has filled in the kind of skeleton for a general MATLAB function. So we just have to fill in this template, and let me give it a title. So let's use a descriptive title, compute root quadratic. And the input arguments are the coefficients a, b, and c of the quadratic polynomial. The output arguments are the roots of this quadratic polynomial x1 and x2. Now for brevity, I will skip on this description here at the top and go straight to filling in the body of the function. So the first thing that we do is we compute the discriminant d, which is defined as b squared minus 4 times a times c. Then based on the value of d, we take certain actions. So for this we will use conditional statements in the form of if and else if blocks. So the first step is to check if d is larger than 0. Well, what do? Well, we simply compute the roots using this well-known formula, minus b plus the square root of d divided by 2 times a. That's the first root, and for the second root we simply replace this plus sign with a minus sign. So that takes care of the case when the discriminant is larger than 0. Now if this is not the case, but if the discriminant is actually equal to 0, well then we are required to print an output message, and for this I will use the fprintf command. The output message should read d is equal to 0 and we have equal roots. Now these roots in this case are both equal to minus b divided by 2 times a, and x2 is simply equal to x1. A final block of our if construction is if the discriminant is smaller than 0. So else if the discriminant is smaller than 0, in which case we print out the message: the discriminant is smaller than 0, there are no real roots, and we return simply not a number. And we conclude our if block with the end keyword. So this should suffice for our function that computes the root of a quadratic, checks the value of the discriminant, and then takes appropriate action. Now let's save this into the current directory with a file name that has the same name as the function itself, and then we can close off the editor. So now we can put our program, our function, to the test by computing the roots of some quadratic polynomials. So let's start with the case where x squared minus x minus 2 should equal to 0. And if you factor this polynomial, it's quite easy to see that the solution should be x is equal to 2 and x is equal to minus 1. Let's see whether our function does the appropriate thing and gives us the correct answers. So I can use the tab button to autocomplete, compute root quadratic, and the inputs are 1, the coefficient with x squared, minus 1 the coefficient with x, and minus 2 the constant. And indeed we see that the outputs, the two roots computed by our program, are 2 and minus 1. Let's look at another example. For instance, the case where we have a discriminant which is equal to 0. For the quadratic polynomial of x squared minus 6x plus 9, this would be the case, and you can check this by yourself. So let's try this out. Compute root quadratic, and the coefficients are 1, minus 6, and 9. And indeed we see that our function returns the message d is equal to 0, we have equal roots, and this root is equal to 3. Now finally, let's try a quadratic equation which has no real solutions. Let's look at the equation x squared plus 1 is equal to 0. Again, we just use the same syntax as we did before. The only thing that changes are the coefficients, which are in this case 1, 0, and 1. And indeed we see our function says that d is smaller than 0, there are no real roots, and we produce the output of not a number as requested by our recipe.